So our next speaker is Xiaochen Zhou from UC Riverside. His topic is about to measure the exploitability of Linux bugs on downstream distributions. Please, Xiaochen.
Okay, welcome to my talk. Here's my Linux kernel security paper, SyzBridge, bridging the gap in the exploitability assessment in Linux kernel bugs in the Linux ecosystem. How this work? Okay. So the first question is Linux kernel really safe? And here's a graph from SyzBot. SyzBot is a continuous fuzzing platform developed by Google. It has started fuzzing Linux kernel since 2017 December, and it has been fuzzing for 6 years. And it has discovered more than 10,000 bugs in the past 6 years. And the red line indicates the open bugs. That means the developer didn't get a chance to fix it. And the total fixed bugs is the green line. And you can see there's a gap between the green line and the red line. That means this many bugs haven't been fixed at the time. And the gap has been gross over the years. It has been slumped back on November 2022, but there's still a huge gap. It somehow indicates that there's a lot of unfixed upstream kernel bugs. You may think, okay, the Linux kernel may not be even safe. But is this really the truth? To understand this problem, we need to understand how Linux kernel, how the structure of Linux kernel. So there is an upstream Linux kernel, which we also can call it Linux mainline. And Linux mainline is the place that the developer push new features and they debugging. And so every developing things is on the Linux mainline. But the Linux mainline is not for the production purpose. So nobody uses the Linux mainline as their daily use Linux kernel or system. Instead, people will use we call downstream distros. For example, Ubuntu is a downstream distro we all know, and what they do is they fork a stable branch of the upstream, and they develop their distro based on the stable branch. And in the stable branch, it's for production uses, they will disable the debugging features, and it's more stable and usable. But like when we talk about kernel security or kernel exploits, nobody wants to exploit the upstream kernel because nobody is using it. The industry, like the Pontoon or other competition, the exploits all targeting the downstream kernels, which is like Ubuntu, Fedora, or other downstream kernels. And if we look at the high-risk bugs, there's another paper, SysScope from Usenix 2023. It says it analyzed more than 1,000 bugs. There's actually 1,170 bugs, and they find 183 of them, they are high-risk bugs. High-risk bugs means they has one is high-risk capability, like UEF write, OOB write, or control flow hijacking, those high-risk capability. This is actually a really high rate. 15.6% of upstream bugs are high-risk. But if you look at the real-world exploits that from SyzBot, it's really limited, like only around 5 real-world exploits that are from SyzBot. But the 183 compared to 5, that's a large gap. Like, does it indicate the remaining bugs, they do not affect any downstream distros? So that we want to answer that question. Therefore, we did a preliminary experiment. We picked 230 upstream bugs and 43 downstream distros. We want to see how many of them they can actually trigger the same bug on the downstream distros. We picked Fedora, Ubuntu, Debian, and SUSE. Actually, we find the result is kind of astonishing. A majority part of the upstream bug cannot even reproduce on either of the downstream distros. 184 has not triggered the bug on any distros, and only 44 of them, they trigger the bug. That's 19.1%, but only by root user. And there's only 2 bugs, which is 0.9%, they can trigger by normal user, which is non-privileged user. That's a really small number. Somehow indicates maybe a lot of upstream bugs, they don't even affect the downstream kernel. So that, but is that really the case? Then we analyze why those upstream POC failed on the downstream. So we picked additional 200 bug distro pairs, and we analyzed their root causes, and we find 120 pairs. They cannot trigger the bug because the distro does not contain the buggy commit. That means the vulnerable code is not even exist in the downstream distro source code. So it's obvious it's not be affected by the bug. And for the remaining 80 that they contain the buggy commit, only 18 of them has been triggered, but all has been triggered by the root user. And for the remaining 62 failed bugs, there's 20 of them, they failed due to the environment changes. We will talk into detail about that later. And there's one failed due to the code context change. Code context change means the vulnerability code, the vulnerability logic has been changed. So in order to trigger that, you need to adapt the code logic. But that's so rare, so in this paper, we do not include the code context change. And for the remaining 41, they failed due to the logic missing. That is different from the no buggy commit. The logic missing is the source code still have the vulnerability commit, but somehow it doesn't compile this code into the kernel binary. But they, even though there are two reasons, but they have the same result, is that the downstream distro does not affected by this bug. So then we did another investigation about like what is the environment changes, and we have categorized into three. The first is preparation step failing. So the preparation step is like when you do fuzzing on the upstream, there is some interface that you have to set up the preparation steps. For example, if you want to fuzz a USB driver, either you plug in a physical USB devices, or you can expose the USB driver interface to the user space. And by saying that, that is the raw gadget. But on upstream, you want to fuzz the USB, so you expose the raw gadget to the user space. But in downstream production kernel, you don't have this debugging feature. So when the POC preparation function try to open this raw gadget, it will fail and will exit the POC. But for some reason, SysBot failed to rule out the unnecessary preparation step. That means this bug may not even relate to the USB. It may not be a USB bug, but somehow it includes this USB preparation function. So solve this problem, we can just remove the preparation function and the POC will trigger again. Another reason is the distro background noises. Because the upstream kernel is for debugging purpose, it's a minimal system and it has less background services running. So when you do a risk condition bug, it's ideal environment to trigger. But on the downstream, there's so many background processes running and competing for the resources, CPU cores or times. So in order to trigger a risk condition bug in downstream, it requires more time and CPU cores. And because the upstream is so easy to trigger a risk condition bug, and sometimes the SysBot can trigger a risk condition bug with one-time effort. So if SysBot finds that, it will even mislabel this bug as a non-risk bug. But instead, in downstream, you have to use a for loop for like a data collision in order to trigger this risk condition bug. Another reason is the kernel module not loaded. In upstream, every kernel module has been compiled into the kernel binary. There's no separate kernel module. But on downstream, like Ubuntu or other distros, you can either compile a kernel module into the binary, or you can compile it as a separate kernel module. You can load it on demand. But if the kernel is not loaded, the module is not loaded, and the vulnerability is located inside the kernel module, you cannot trigger the bug until you load the kernel module. So this gives us two questions. Can we trigger the bugs on downstream by adapting their POCs, and can we trigger them without requiring root privilege? To answer the first question, we propose the POC adaptation. The first is the preparation step failing. We have to investigate which preparation step is not necessary, and we rule out the unnecessary preparation steps. And for the distrong background noise, we will force to free the occupied resources. These resources could be occupied by kernel services, and we want to force to free them so our POC can use them. And we will enable the for loop for every POC, even they are not risk condition bug. Because doing this, we can force the data collision in every POC in order to trigger the risk condition bug. For the third question is a necessary kernel module not loaded. We use kernel trace to identify the missing kernel modules. On the right-hand side, we have two kernel traces. The upstream kernel triggered the bug. You can see the deviation start from the km state notify function. On the upstream, it triggers xfrm send state notify. However, on the downstream Ubuntu, it does not trigger the bug, and this km state notify calls another function, which is the pf key send notify. So by comparing their kernel traces, we can node from node 3 to node n, those functions does not exist in the Ubuntu traces, and we will find the associated kernel modules that have those functions, have those missing functions, and we will load those missing modules by using modeprobe. Modeprobe is a user space utility that can load kernel module, but it requires root privilege. We will get into modeprobe later. So we solved the triggerability issue. The other question is, can we trigger them by normal users? So this is related to the privilege downgrading. If you still remember all the 18 triggerable bugs, we can only trigger by root users. So we find that the kernel have two kind of like privilege check. The first is the kernel capability check. We want to know which capability kernel uses, and we're monitoring the low-level kernel function unescapable function, and we will get all the kernel capability is try to grant it, and we force the POC to use the kernel namespace to grant such capability if they can be granted through namespace. And another is kernel privilege operation, like release occupied resources or mounting file system or using modeprobe to load kernel module. They are related to our previous triggerability adaptation. But however, releasing kernel occupied resources require root. For example, you want to unmount something, or you want to free a loop devices, it requires root privilege. And mounting file system also require root privilege. So they only left us the modeprobe problem. So we're thinking, can we call modeprobe by normal user? So what is modeprobe? Modeprobe is a user space utility program. It can load kernel modules. And eventually, when you call modeprobe, it will get into a kernel space and call the initial module kernel system call. And this system call will call a main initial module function. This function checks whether you are a root user or not. If you are not a root user, it will exit the program and return an error. If you are a root user, it will load a module. For example, module A is a module you try to load it. But when we look at the kernel code, we realize there's another function, another kernel function. It can do an opcall to call the kernel module. This request module function is in the kernel space. It do an opcall to the modeprobe, and modeprobe will load the kernel module for us. So, and this function is inside the kernel space. So we're thinking, is there any system call can reach the request module without root privilege? And for example, ideally, syscall A can reach this kernel function, and this kernel function load the module A. And we might find another function can load module B, and find another system call load module C. If that could happen, and look at the flow we were thinking about, if we can use fuzzing to do this. And by using fuzzing, we instrument the request module so we can know which module to try to load it and whether it requires root or not. And we can also give feedback to the fuzzer and generate the concrete test case for us. By doing this fuzzing, we actually find a reasonable amount of kernel modules that can be loaded through normal user. One example is the previously we find the XFRM user module is missing. You can do it either through modeprobe, but this requires root, or you can simply call this system call. It only requires normal user privilege, but they do the same. They both load that XFRM user module for you. That's privilege downgrading. And now we have two components ready. One is the bug reproducer, which solves the triggerability issue. Then there is the privilege downgrading, which solves the privilege issue. If either of them failed, we will have the failure analyzed, and we apply the adaptation accordingly and have a new POC and do everything all over again. And then we have two evaluations. The first we want to evaluate the triggerability adaptation, like how many upstream POC we can trigger on downstream. So we have 230 upstream KSON bugs ready and 43 downstream distros. Before applying SyzBridge, the upstream POC can trigger on Ubuntu Fedora Debian, they can trigger 55, 58, 33, 29 bugs, but they can only be triggered by root user. For the normal user, it's so little, like only 2, 3, 2, 1 can be triggered by the normal user. But after applying SyzBridge, we improve the result. We improve the root triggerable result by 61% and the normal user triggerable bugs by 13 times. That's a really good result. And so the triggerability issue has been solved and has been improved by SyzBridge. The other evaluation we did is we want to see the exploit assessment pipeline. This time we choose 282 upstream high-risk bugs, means they have at least one high-risk capability, like counterflow hijacking or arbitrary address write. This time we also did on this for downstream distros, and the normal user triggerable bug is even lesser at 1331. That somehow indicates, because like exploitable bugs require high risk bugs, and there's only so little bugs that can be triggerable by normal user. So that's kind of indicate, previously we said only 5 CVE in SyzBot, and that's kind of proves that's true. But after applying SyzBridge, we find there are actually so much more bugs that can be triggered by normal user, high-risk bugs, or like exploitable bugs that can be triggered by normal user. For example, Ubuntu, there's only 1 before adaptation, but we improve it to 35, and 3, and Fedora is 3 to 50. Well, in this table, we have a snippet of the complete table, and for example,
I guess we need to move quickly.
Okay, sorry. So for the interest of time, we'll just show that there are some of them that requires the adaptations, and the key takeaway is that the upstream POC often failed on downstream OS, but it does not imply that downstream are immune from the upstream bugs, and the upstream POC can be transformed to downstream valid POC through varied adaptations. And a similarly high-risk privilege POC can be downgraded to low privilege, and SyzBridge has found more than 50 bugs are likely exploitable at least 1 downstream distro, whereas only 5 were recognized as CV in the past 4 years. And that's all my talk, and thanks for listening, and I'm ready to take questions.
Okay, I think we can afford 1 or 2 questions.
Thanks for your talk, Mikra Chaudhary from NUS. So a few years ago, we did a study of the patching, means the bugs that get patched in the main line. It seems a lot of them remain unpatched in the other distributions of Linux. So what your work shows is that the threat or the gap because of this is even more enhanced by your work, because the vulnerabilities that can be exploited in the main line, you can now exploit them in other downstream distributions. So it's just a comment that this threat is very much there, and what we found in our study, which appeared in 2021, in ISTA 2021, is that lots of these, so this patch backporting problem, nobody is looking into. So I just wish some people, instead of working on fuzzing, would look into this patch backporting problem, and your work shows that the threat is even more. So,
thank you. That's indeed a problem. Actually, we find that a lot of fixed bugs on upstream, the downstream still remain unpatched. We actually test a bunch of them and find there are a reasonable amount of them, they still can be triggered on the downstream, even they are fixed on the upstream. Yeah.
Okay, maybe last question.
Hi, Roland Yap, NUS. I don't know if you follow the State of Linux kernel talks. I think if you look at the one from last year, 2023, it discusses some of these issues with downstream, upstream, any year, and so on. So if you haven't looked at the talk, I suggest you take a look at it.
Okay.
If you have looked at it, then you probably know the issue. Another comment is that I wonder whether some of these problems are due to configuration. Because Linux configuration is quite complex, and maybe some code is not there because the downstream kernel has a different configuration than the upstream.
So for the configuration, for the upstream, we strictly follow the SyzBridge configuration. It will provide a configuration. We strictly apply that configuration. For the downstream, we use the default downstream configuration. We do not we enable KSON or some other sanitizers in order to catch the bug, but we do not.
But the change of kconfig might mean that certain code is no longer there.
But we believe like if you just enable the sanitizer, it does not like change the code. I don't think it import that side effect if you just enable the sanitizers.
The config does change the code.
It changed the code, but it like imports some sanitizer features. But I don't think it will cause the bug not trigger.
I'm just wondering whether that's
that might be. I mean,
might be
but we don't
cause.
find any evidence to support that.
The configuration is complicated, so it's a bit hard to know.
That could be. I mean, yeah.
Okay, let's thank our speaker one more time.